So, good afternoon. Because of the problem of projection in the morning, therefore let me have the compensated class for you currently. Well, in the following, after the calculation of queuing delay, now let us have the real internet delays and also try to show the roots. Well, so this one, what do real internet here, real internet delay and loss. We use a program. The current program we call trace route. You can use a trace route in Windows system or maybe Linux system, and this program can provide you the delay measurement. Of course, it can show loss ratio for sure. How we can reach it? Actually, we can send 3 packets. The 3 packets we call probing packets. So we can send 3 probing packets. That says we have 3 probes here. And the probe packets can reach the next router, next one, and the others. Look at these. All right, so we have the 3 probing packets. Because of 3, so we have the measurement, 3 delay measurement. Well, the next one and next one to the end, actually the destination. So we have the major delays. Well, we have delay and the others. But sometimes we don't have any record. So we have the asterisk to denote no record here. Well, based on no record or maybe 1 record, actually you can have a loss. For example, here, this one, what is the loss probability or loss ratio? 0 received, so we have 3. So actually, if we check the later we can code this is successful ratio. The success ratio is 0. And of course, the loss ratio is 3/3. So you can have the loss ratio. Well, using this one to check some possible scenario, well, almost reasonable increase. But why we have the abrupt increase from around 20 milliseconds to 100 milliseconds? Because we have transoceanic link. Because transoceanic link, so we have a huge increase in delay. After that one, we have the reasonable increase in delay. So this one is still okay. And finally, maybe some cannot be received. So we have asterisk to denote no record there. No record there. So that says the packet, the probing packet, have been lost. Because of lost packet, so we can have the calculation of loss ratio. For example, the previous one, we have 100% loss for this case and this case. Well, so that is the real measurement about delay and loss. And right now, let us have the further discussion about the packet loss. Why we will have loss? If we want to talk about that one, first of all, we have a queue. Well, queue, you should understand previously we did have a different name that says also known as AKA, also known as buffer. So before we have the transmission, processing, and the others, actually the packet will be put into the queue. If the buffer is full, so buffer or queue is full. Why it is full? Because of finite capacity. You see, we have a finite capacity or finite waiting room. If we exceed the final capacity, then the packet will be dropped, and then we have packet loss. So here you can see we have the packet put into the queue. However, if it's full, then we have packet loss. So we have lost packet here. Well, this one, you see, full queue, then we will have a packet dropped. That says packet lost. Well, about the lost packet, then what to do for these? Actually, they will be retransmitted if indeed we care about the accuracy of the information. If no, sure, we can have the actually try to recover the packet possibly. If so, then it won't be necessary to retransmit it. Well, about the transmission, later in the other chapter, we will have the detailed discussion if we care about the completeness of the message. Well, we have the delay. We have 4 components. Then we have loss. And of course, we can have the real tool to have the measurement. And last one, we have the throughput. Previously, I didn't know the throughput. For example, this one. We mentioned this is a throughput. Zero throughput and 100% loss. So throughput related to loss for sure. Currently about the throughput, we don't have that ratio. Actually, the throughput here, indeed, we try to have the bits passing through over the time, so that we have the unit like this, bits per time unit. Well, the throughput says, if possible, we want to know, measure in time, what's the quantity in bits. Then we can pass through, or we observe that bits pass through some specific node. All right, node. So we want to know which rate. So here it's rate. Which rate we can allow the data passing through the specific node. Well, about that one, of course, you can have the inspection at the router, and so that you can observe at any time instant. So any time instant, then we have the instantaneous throughput, or maybe we have a time period to measure the rate, so that you have the average throughput. Well, if we can have the given information, later we have the further throughput we want to derive. So what kind of throughput we want to derive? This one. Well, to have the division throughput, for Taiwanese, maybe you want to know what's the name in Chinese here. This is the name in Chinese. All right, and if we want to have the English definition, this one, amount of work or maybe bits done in a particular period of time. You see, particular period of time. Well, but a particular period of time, so we care about the average value. But actually, we can have the instantaneous throughput. And right now, we want to have the end-to-end throughput. So here, we want to consider end-to-end throughput. So right now, we want to have the end-to-end throughput. And how to have the end-to-end throughput if we assume the perfect transmission. So look at this. If we have the perfect transmission, this one, we have R1 and R2. So we have the capacity. Previously, we have the capacity. If we assume the perfect transmission, that says we can reach the rate for sure, right? Because we can reach the rate for sure. And here R1 equal to the RS and R2 equal to RC. It doesn't matter. If we have the rate, that says the capacity. And right now, you see, something like we can have a concept using a pipe. All right, using a pipe. And a pipe, so of course, we have the possible capacity. And the capacity actually, previously, we used the transmission rate. And right now, if we have the transmission rate and using the pipe to consider the end-to-end throughput, so how to have the end-to-end throughput? Actually, the end-to-end throughput, try to find the minimum rate. First one and the second one. All right, so we have the minimum. Minimum says we try to find the bottleneck. Well, previously about the end-to-end delay, we also use the concept of a bottleneck. Yes, it's true. The bottleneck here, the same as the previous bottleneck we mentioned for the calculation of the end-to-end delay, because we consider the transmission delay there. And here actually we have a capacity. This capacity can be related to the transmission delay for sure. So we consider the bottleneck of the link, and bottleneck of the link, then we can have the capacity, and that capacity serving as the end-to-end throughput. All right, so here we want to that we have the further derivation about the end-to-end throughput. Well, I don't have that one. Try to find the end-to-end throughput using the operation of minimum. Well, if we have the assumption R sub S lower than RC, so here this one smaller. And here this one smaller. And so finally find the bottleneck where we have the bottleneck, this one, and where we have the bottleneck, this one. And here this is a server, so we call it R sub S. And this is a client, so we have R sub C. So for this case, the throughput should be this one. And for the second case, it should be this. And that's all. So follow the operation of a minimum, then we can find the end-to-end throughput. Well, end-to-end throughput, actually we try to find the capacity for the bottleneck link. Right? That's it. Well, in fact, for the real network, normally we don't have the maybe link plus link, and so that we reach the destination. Normally we have that case, but we will share. So within the core of the network, we will have the capacity shared by each links. And virtually, if we have multiple connections, here we have multiple connections. And assume we have the RC and RC and RC here, not the share one, because we have the individual capacity for each server or each client. However, for the network, assume we have the possible capacity shared by 10 connections. So why we have the share phenomenon? Later in chapter 2, we have the possible scenario so that we can know why we can have the possible situation to share the bandwidth. However, to share, so first one, middle one, and the final one, so we can have an operation of a minimum. Still, we can have the capacity for the possible link. And right now, we can find the bottleneck using this. If we have the minimum operation, and then that's done similarly. However, if we want to find where we have a bottleneck, it says, oh, okay, normally it should be client or server. Why? Client and server actually we don't prepare a bundle of bandwidth or the transmission rate. So normally, either client or the server will be the bottleneck. So that's why we have the possible situation. Well, so this is the performance, talking about loss, delay, and throughput. And let's go further to check network security quickly. And actually, we don't have the detailed discussion about the network security. If you are interested in network security, you can take a specific course addressing network security. And later, we try to have the brief introduction to the field of network security. Well, so the field of network security will want to check how bad guys can attack computer networks, or how we can defend against the attacks, and how we define or design the architecture, and so that we expect the architecture will be immune to attacks. That says if we have the architecture, then we won't have any compromised component within the architecture. Of course, we expect that one, but is it true? Normally not true, but at least we try to have the possible architecture, and so the architecture are immune to attacks. Well, now let's get back to talk about internet. For the original design of internet, it is not designed with security in mind. Why? Within all components are trusted components. And likewise, we can think all users are trusted users. So that's why we don't keep security in mind to design the internet. Because of this, then internet protocol designer will provide security using the manner catch-up. So if we find the part of the network has been compromised, that access has been attacked, then we will have the catch-up. With the catch-up, then possibly we expect the newly designed architecture will be immune to the attacks, but it doesn't mean to all the future attacks. No, because impossible. Well, so this is the possible consideration in the internet. And likewise, for the other types of network, we will use the similar way. Well, for security consideration, only consider for example, for internet within the network layer. In fact, no, actually, in all layers, we can consider network security. So we mentioned this, network security consideration in all layers. Well, bad guys, how we call bad guys in the internet? Normally we call malware. Malware is the bad guy in the internet or in the network. And malware, how we have the types of malware, it can be virus, it can be worm. And here we have the possible definition for virus or worm. You can check them for yourself, and then you can easily understand it's a malware, or maybe we have a type of virus or a type of worms. And for specific purpose, spy, serving as a spy, then we have spyware. Or we call spyware malware. And spyware, then it can recall keystrokes, websites visited, and information for that site. And for all components in the internet, if some of them are compromised, we call compromise and compromised, then it is infected. So some hosts or some nodes are compromised, then they are infected node. And infected node will be enrolled in botnet. And so that botnet forms a node that can compromise the other node. Well, so we call it a botnet. And this botnet will be used for spam, for distributed denial of service, or we have a shorthand DDoS attacks. So why we mention botnet? Because botnet can be used to have the possible attack, spam, and denial of service. Specifically, it is a distributed denial of service. Well, and previously, we didn't know in the network, computer network, we have malware. So this is the definition for malware, computer software, and they are designed to damage some component of the network. And we have the meaning in Chinese. Well, denial of service, how to breach the denial of service attack. This kind of way to achieve the denial of service. For the possible attacker, it should select the target. For example, the target here is a server. And how to have the denial of service? We have nodes from the botnet. All right, nodes from the botnet, then they can serve as the attacker. Right? Serve as attacker, then many attackers can request the service. And so that we have the DOS attack. Well, select a target, then we send the request to the server. So send packet to the target to the server. And how we have the nodes or hosts? Actually, I don't know. Botnet, we will have the compromised host. And the compromised hosts enroll in the botnet, and then those hosts can serve as the attackers. So this is a scenario like this. We will have the DOS attack. Well, so this one. And that is the DOS. And actually, we can get the information, and we call it the packet sniffing. Why we can have sniffing? Sniffing actually, what it means, this one, actually use your nose to smell. Here, smell. But we use it in the internet to let you know we will have to obtain the information from the packet. And the next one, we have promiscuous. And promiscuous, this one, mix them. So mixing or mixed. Then we have a promiscuous situation. So where we have the promiscuous situation in the internet, for the interface, all the possible data will be put together. So this is a promiscuous mode. And promiscuous mode, then anyone can listen to or check the content of the packet because of the nature. Broadcast media. Broadcast media with the share concept. Because of the share concept, so we can know the content of the packet. For example, finding the source destination, and of course we have the information within the payload. Well, this is the possible situation done by the attackers. And normally we have a software. This kind of software we call Wireshark. Wireshark, is it a good guy or bad guy? Actually, it's a good guy, but we have name Wireshark. So we have a fins of a shark. So that says we have a Wireshark. Using the Wireshark software, we can have the packet sniffing. And you can have the further inspection. And Wireshark software provide you the free software. And so that you have the free packet sniffer. You see, packet sniffer. Specifically, we emphasize it's a packet sniffer. Well, so that's the sniffing. And next one, we may have these. Fact. Fact here is not real. Or not eligible. So not real or not acceptable identity. So identity, what kind of identity in the internet? It's an IP address. So IP spoofing. Spoof says here. This one, spoof. Try to ask someone to believe your IP is true one, but it is indeed not true. So IP spoofing. And previously I already have the content. It is called payload. So you have these. Well, actually we have a payload. Actually here we have a payload again. So we try to have the source IP spoofing. Of course, you can have the source IP spoofing to that the destination know, okay, you are a real IP. In fact, no, not correct. All right, that's all. So this is the network security. We try to have the briefing to network security. And let me go to have the discussion about protocol layers. And to have a protocol layer, then we need to have a reference model. So why we want to have a protocol layer based on the reference model? Because networks are complex. So we can split the maybe all possible components into the individual component. For example, we can have a host. We can have a routers, we have a link, and the others. So we have a question. Is there any hope of organizing the network using the specific model? Yes, we have the reference model. With the reference model, then we can have the split layer, and the split layer we call protocol layers. And so that it will be easier for us to address the individual one. And here we have an example from traveling. Well, to have the travel, normally you should buy a ticket, then you need to have the baggage sent to the counter. And once you send it to the counter, then you can go to the gate to wait for the airplane. And then you can go along with the airplane so that you have the takeoff, and so that the airplane will go to the possible next hub or the destination. And for the other side, we will have finished routing to the destination or maybe the intermediate node. And then we have a landing because we need to go there. Maybe it's the destination or maybe no. And then it's get to unload your baggage or luggage. And finally, if you have any complaint, then you will have the stage of a complaint. And here we show you the possible mission or task and how to have the possible layer for all the tasks here. It is a possible layer for traveling. And likewise, we can use this concept to have the organization of the travel so that we have a layer. Here we have a layer. And we have a layer for traveling if we don't care about the airport at one side and airport at the other side. Well, so we have the possible requirement of layers. Requirement for layer, why? Because we want to have some service defined within the layer. And so that we can make the whole task a bit easier. And so that you just focus on the individual mission within the layer. Well, because of this, we have the old layers here. And because of the layering, so we have a question. Is it possible to have the similar arrangement for the network? The answer is yes. And because of this, so we can have layer. And right now, let us get back to giving you the reason why we should consider layering. Because we want to deal with complex networks or complex systems. So we will have the possible layer and possible layer to form the reference model to ease the simple discussion. And so that we have a module. And then modularization is maintenance, updating, and the others. And so that if we just want to change one of layer, then that layer can be transparent to the other layers. However, if we have a possible layer, is it harmful? Sometimes yes, probably yes. So it doesn't mean we always have the benefit. Sometimes we have the harmful effects. However, we still think it's necessary to have the consideration. Well, and if indeed we want to study the network, specifically the internet, we will have the following internet protocol stacks. Here we have 5 layers. All right. About the discussion, I think left to us to have the further discussion next week. And let me stop here. And so that, yeah, almost the time allow you to have the possible content reach within the week. All right. So for the remaining discussion, I will reserve them. But before we go, I already have the name of the 5 layers. Application layers from the top. And the transport layer, network layer, data link layer, and physical layer. We have the 5 layers. As for the other details, I will continue next week. And hopefully we can go through and complete the discussion for chapter 1. All right, so that's it. Internet protocol stack, and we will have the further discussion next week. Well, because of the actual class that says a compensated class, I think I won't ask you any questions. And so that let me stop here and see you. Bye-bye.